Since the first petrol engine was constructed at the end of the 19th century, no significant changes have occurred in its operation for the next 100 years. The carburetor as an element for forming the air-fuel mixture was an inviolable and irreplaceable part of gasoline engines. With the advent of fuel injection, there were changes in the processes of mixture formation and electronic control of engine operation. Since then, petrol engines are more powerful, reliable, economical, and environmentally friendly. This series deals with the injection systems of petrol engines. Through this and the following lessons, you will be introduced to all injection systems from the carburetor engine to this day. You will find out how they look and function, how to maintain and adjust petrol injection systems, as well as their elements from the intake manifold through the engine to the exhaust. To successfully service an engine, you need to know its operation and the injection system that serves it. Knowledge is a prerequisite for your efficiency at work. Reasons for introducing fuel injection. Why did the car industry give up carburetors? What were the motives for introducing injection? What prompted the constructors to replace a relatively simple device such as a carburetor with an injection that performs the formation of the mixture in a completely different way? Two conditions were crucial for the introduction of injection. First, due to competition, manufacturers wanted to improve the degree of utilization of the gasoline engine to reduce fuel consumption. And the second is the legal norms on the control of exhaust gas emissions that were inevitable and binding. Carbureted engines could not comply with emission standards, but could only do so by using electronic engine control and fuel injection. These conditions forced engine manufacturers to look for an acceptable solution. All constructive changes to the engine are made to increase efficiency, and this is achieved only in two ways: by better management of the combustion process and mixture formation, and by reducing losses in the engine operation process. By introducing and improving the injection system of petrol engines, the following is obtained: better engine characteristics, more powerful engines, more economical engines, more ecological engines. The specific advantages of electronic engine management and injection are: service support for the vehicle buyer. The introduction of electronic engine operation control has facilitated monitoring and servicing through vehicle diagnostics. Product protection. Electronic components are difficult to copy and are therefore safe during replacement, unlike mechanical ones. Requirements off the car market: faster, more powerful, more efficient engines with reduced fuel consumption are required, which leads to competition in the development between vehicle manufacturers. Regulation on exhaust gas emission control, which decisively influenced the accelerated technological development of the injection system at vehicle manufacturers. Without the introduction of mandatory regulation on exhaust emissions, manufacturers would not independently invest enormous funds in the development of electronic systems for controlling engine operation. To understand the working principle of the injection system, it is necessary to understand certain parameters of the engine on which the control of the formation of the mixture depends. To explain how the injection system works, we always use a four-stroke, four-cylinder petrol engine. The operation of a four-stroke engine consists of 4 cycles: intake, compression, combustion, and exhaust. During the intake stroke, the intake valve is open. The piston moves towards the bottom dead center, the cylinder volume increases, and the prepared air-fuel mixture is sucked in from the intake manifold. The mixture temperature is relatively low, below 90 degrees Celsius. During suction, there are certain obstacles to the flow of the mixture, and the pressure is slightly lower than atmospheric, around 0.9 bar. When the piston reaches the bottom dead center, the intake valve closes, and by inertia it moves towards the top dead center, reducing the volume of the cylinder, that is, compressing the mixture. It's a compression stroke. During compression, the pressure and temperature of the mixture increase. The temperature can reach 600 degrees Celsius and the pressure up to 15 bar. Near the end of the second cycle, a spark appears, igniting the air-fuel mixture. The flame front of the burning mixture expands, causing a sudden rise in temperature up to 3000 degrees Celsius and pressure up to 50 bar inside the cylinder. The high combustion pressure in the third stroke pushes the piston towards the bottom dead center, creating engine drive and vehicle motion. When the piston moves back to the top dead center, the exhaust valve opens, through which the burnt gas is ejected from the cylinder through the engine's exhaust line. The exhaust gas is hot, and due to the damping in the exhaust, the pressure in the cylinder is increased. During the four-stroke combustion cycle, the crankshaft turns twice while the camshaft turns once. To understand the operation of the injection system, we need to know what torque and power are. A torque is a twisting or turning force. It is based on the force pushing one end of the lever to produce rotation at the other end. A torque is used to tighten and loosen bolts and nuts with a wrench. The magnitude of the torque depends on the strength of the thrust force and the length of the lever. The torque is the product of the force and the length of the lever. To create a torque, we use the force of the arm muscles, which is converted into rotation via the wrench handle. Often, the created torque is not enough to unscrew a nut. Since we cannot increase the force of hand pressure, we need to extend the lever of the wrench to create a greater torque sufficient to unscrew the nut. So, by simply lever extension, we increase the torque. In the engine, the pushing force of the piston is converted into the torque of the crankshaft and the drive of the vehicle via the connecting rod as a lever. The turning force applied to the crankshaft is the torque of the engine. The crankshaft then applies rotational force to other components, such as the gearbox and pulley. In a naturally aspirated engine, the combustion chamber is only partially filled with the mixture due to the resistance of the air flowing through the intake manifold. The maximum engine torque occurs in the range of low to mean engine speed when the filling of the cylinder with the mixture is best. Then the engine is most efficient and has the lowest fuel consumption. As the engine speed increases further, the torque drops. From the graph, we can see that with the increase in the revolutions per minute, the torque increases and reaches its maximum value at 1700 RPM. Because then there is a maximum filling of the cylinder with the mixture. As the revolutions per minute increase, the torque drops because the time required for charging is reduced. Engine power is the amount of mechanical energy at the engine output obtained from fuel per unit of time. Engine power is the product of torque and engine speed. The power produced at the crankshaft is the gross power of the engine. Additional devices such as alternator, air conditioner, radiator fan, water pump, and others consume part of the generated power. These devices take away 25% of the gross power generated at the crankshaft, and what is left is the net power of the engine. As the revolutions per minute, the engine power increases, and unlike the torque, the maximum power is achieved at a higher speed. For the given engine, the graph shows that the maximum power is reached at 3,500 RPM and then drops. The third graph indicates the engine power used to overcome friction and resistance within the engine itself. Efficiency represents the percentage utilization of fuel energy to start the vehicle. One of the main goals of introducing electronic control of engine operation and injection is to reduce fuel consumption. Carburetor engines had poor efficiency, which was up to 35%. Modern petrol engines go over 45%. That's still a very low power utilization to boot. Where are the losses occurring, and where are improvements possible in raising the vehicle's efficiency? First, let's see what the losses are on the vehicle. The petrol engine is used to convert fuel energy into the motion of the vehicle. At the start, the biggest losses are in the engine, which is over 60%. A large part of the energy is spent idling the engine when the vehicle is stationary. A part of the energy is used to operate additional equipment on the vehicle. Then, during startup, due to the friction of the transmission from the engine to the tires, certain losses occur. In the end, the vehicle itself needs to overcome air resistance, and losses occur due to tire slippage, inertia, and during braking. Vehicle manufacturers are constantly trying to find adequate solutions to reduce losses to obtain a more efficient vehicle that consumes less fuel. An ideal machine converts energy from one form to another without loss. The steam engine had an efficiency of 12%. The most efficient machine ever constructed is Tesla's electric motor with an energy conversion efficiency of over 98% and a transformer of almost 100%. According to this, petrol motors have low energy conversion efficiency. The biggest losses are thermodynamic losses that occur due to engine cooling and amount to about 45%. Then there are heat losses due to engine radiation and in the exhaust gas. We have losses due to maintaining the composition of the mixture at lambda equals 1, pumping losses, losses due to friction and the drive of additional equipment. In the end, only 13% of the invested fuel energy remains for the useful work sent to drive the vehicle. Little fuel energy is used for what we want, which is driving. Petrol engines are internal combustion engines that convert fuel energy into mechanical energy in thermodynamic processes. The spark ignites the mixture of fuel and air. Combustion inside the cylinder rapidly increases the temperature up to 3,000 degrees Celsius and the pressure up to 50 bar, which is used to push the piston and create mechanical energy. However, the temperature is too high and can quickly destroy engine parts. That's why there is an efficient cooling system that lowers the engine temperature to 100 degrees Celsius. Most of the generated fuel combustion temperature is extracted from the engine and discharged into the environment through the radiator. A large part of the generated heat energy is thrown out, reducing the engine's efficiency. Also, part of the heat is transferred by the radiation of the hot engine and the other part is thrown out through the hot exhaust gases. So far, no one has been able to use these losses to create useful work. They partially reduce the losses by increasing the engine operating temperature and with direct injection and stratified operation mode. Other losses are reflected in the fact that a part of the generated mechanical energy is spent to cover defects in the engine operation and for the operation of additional devices on the vehicle. About 10% of the generated energy is used to overcome pumping losses. The petrol engine cannot freely suck air into the cylinder but needs to use part of the energy due to the damping of the flow through the filter, the throttle, and the narrowing of the intake valve. Also, in the fourth stroke, it cannot eject the burnt gases smoothly but uses part of the energy to forcibly push them through the narrowing of the exhaust valve, the catalyst, and the silencers in the exhaust pipe. In this lesson, we saw what the reasons were for the introduction of injection, as well as what the problems were in the operation of the AutoEdu engine. In the next lesson, you can learn about the basic parameters of the petrol engine, as well as the elements of the injection system in the air intake section.